Hello. Welcome to IMDM 498I, Intro to Motion Capture System. Today we'll be covering camera and calibration. First, let's look at different types of motion capture system. We have classified the motion capture system based on the different modalities and the energy it uses. The first one is light-based. Light is perceived using sensors called the photosites. These are receptors that change voltage based on the intensity of the light that is perceived. And by changing different color filters and combining all of them together, it is able to perceive color image. An example of that is digital camera on your smartphones, machine vision cameras. These are all examples of your digital camera. Second one is IMU, or Inertial Measurement Unit. These are the same sensors that are in your phones and your watches and your video game players. They have something called a gyroscope, accelerometer, and if it is more than 6 degrees of freedom, then they might also have magnetometer, which is your digital compass. Gyroscope measures your angular velocity. Accelerometer measures your linear velocity. Magnetometer measures how are you oriented with respect to the Earth. A motion capture suit called Xsense is an example that uses IMU. And in fact, recently, Dr. Kate Landenheim used this for a project where she wore this and recorded her falls. And each fall was graded by her guests and students on how committed she was to the fall in order to gather data on what a committed fall looks like. And by using the data and the perceived commitment of the fall, then we were able to generate novel animations of different kinds of fall using this data and the motion capture data that we collected. Next, we have mechanical system. Some sensors are flex sensor, which measures how much something is bent. Other one is an optical encoder, and this measures how much something has turned. So by applying this in a joint of, for example, an exoskeleton, you're able to measure what the pose of a person is. You can also use this to know this is an actual exoskeleton, a powered exoskeleton, but you can imagine just embedding these kind of sensors throughout our body to measure how someone is moving. For example, flex sensor is heavily used in gloves. Magnetic ones. You know how a magnet works, and in this case there are sensors that can observe changes in magnetic field, and by placing these sensors or magnets on your body, where you are able to measure how your body is moving by measuring the changes in the magnetic field. Similar to the magnetic field, you can also use radio waves. In this particular research paper, they use Wi-Fi signal to be able to track a person even behind the wall where they were moving. And then there are more hybrid methods where they combine optical and IMU, for example, using depth in case of Connect, and using AI to do a pose estimation using RGB and depth in this case actually. And there are other motion capture labs that use marker-based system along with some neural network. In our case, we use initial pose 2D pose estimate from monocular camera, and then we combine with the audio. And where this comes in handy is trying to understand somebody's pose while they're playing an instrument. We know that only way to produce the sound is because of a motion. So if we can learn what the inverse relationship is, then by using the audio, we are able to infer better pose estimation. Now let's go back to digital cameras. You have two major parts to the digital camera. First is the lens in the front that captures the light and projects it into the sensor. And the sensor, like we talked about earlier, will sense changes in intensities of light and colors. There are two kinds. One is called a rolling shutter. Here's an example of deformation due to a rolling shutter. Now, why is this? So the way a rolling shutter works is at any given time, it takes a capture of each individual pixel or individual row. In delta time or small amount of time, it moves to the next one, and it tries to do this as quickly as possible. The reason you do this is it makes the implementation and cost of the camera much cheaper. However, when things are fast moving, such as in this case the tennis, you get these kinds of deformation. So clearly, this is not an ideal choice for a machine vision motion capture system in a lab where you might be moving very fast. In order to avoid that, we use something called a global shutter. Now, these are more expensive because you need to be able to route all the packets of each individual sensing data. You need to have asynchronous sensor for asynchronous reading of each of the sensor that you might have in the camera. So as you can imagine, that gets costly. Now coming back to our digital camera, let's look at the lens again. So lens has, at least in our motion capture lab, our lens has 3 settings. First one is the zoom. It lets you zoom in and out. Third is the aperture. It lets you control the amount of light that's coming into the camera. And third is the focus. You can use this to change the sharpness of an image and adjust the focal length. Now, by changing these values, the image will look quite different, and there are certain parameters that needs to be adjusted. For this, we do a calibration. For example, there is something called an intrinsic calibration. This is calibration of adjustments we need to do based on what is happening with the lens and the sensor. So intrinsic meaning in the camera itself. So here you can see in this image, the image is distorted, right? And to correct for that, we need to compute the distortion values so we can rectify the image. Second is a focal length. So depending upon the focal length, the image can look quite different, even though the camera is placed at the exact same place. So we also need to know what the focal length is to understand what is really happening in the world and what is the camera really seeing. And there are other sensor parameters. One is skew. If the sensor is not perfectly placed, which is very, very difficult to do, the image might come out slightly skewed, and we need to correct for that. And final one is optical center, or it's also called the principal point, which is the center of the image sensor. Now, it is very difficult to place the image sensor perfectly in the center of the image and center of the lens, so we need to compute for what that slight shift is, and in X and Y direction, and that is your optical center. Having that said, let's look at a marker-based system. In a marker-based system, each marker is coated with this retroreflective paint, and when a motion capture camera such as a Vicon, they will broadcast an IR beam, which will reflect back into the camera, and that's what it will detect. So what does this look like to a Vicon camera? So you will see everything will look dark, but the only part that reflects back the IR, it'll light up bright. So in this case, the motion capture marker will appear as a white blob. So in given image, we know exactly the position within the image, what this is. And then you repeat this with an additional camera. And then you keep doing this with more cameras. So now each camera detected it in a different place within individual images, right? Because they're all placed at a different location. Now, in order to compute what is its 3D position, we will need to know how are the cameras located with respect to each other so we can compute for the 3D position of the marker. In a markerless system, it is something similar, except instead of using a marker, each camera will compute some key points within the body, and in this case, it is computing a 2D pose of the person. And by taking all the poses from different cameras and combining using extrinsic calibration, you're able to then get the final 3D pose. And now, what is an extrinsic calibration? Now, extrinsic calibration is outside of the camera, and it is how is the camera located, both position and rotation, with respect to the world coordinate system. Over here, our world coordinate system is marked with the green plus sign. That will be considered our world's, so that's your origin. So each camera's extrinsic will be what is its rotation and position with respect to the world origin. Similarly, that was Vicon, and now this is Capture2. In Capture2 also, the world coordinate system is marked by the plus sign, and all the other cameras, you can see the orientation and position with respect to the world coordinate system. Let's go ahead and take a look at how we calibrate it. Let's start with marker-based motion capture system calibration. We will be using Vicon Nexus. All right, what we're going to do now is calibrate Vicon. Okay, so for calibrating Vicon, first thing we're going to do is we need to mask. Now, what mask does is if there are any reflective markers or any reflective surfaces or any other cameras that it's seeing which are not cameras, it needs to know ahead of time so it can ignore it. So what we're going to do first is be in a connected mode. We can see that these cameras are live, and first thing we're going to do is start masking. So you just sit here and wait a few seconds, and once the pixels have turned blue, the ones that it detected as potential markers or IR reflection from somewhere, we can just stop. And then at this point, this is our reference camera being shown here, and then these are our Vicon IR cameras. So we will start to calibrate. And to
Calibration started.
What we do use, this is a wand, and this is what we will be using. First thing we do is turn it on, and it has this IR lights that is being displayed, and as we move about in a shape of infinity shape, or number 8, and we want to point it to all the cameras as we do this. And as you see on the screen, it's drawing, and all these cameras turn these. You see these turning green from purple. That means it's done. And this camera is purple still. This one. So I'm going to make sure that this camera has sufficient coverage. You can see on the screen too, coverage.
Wand wave complete.
Done. Let's make sure that this camera also has sufficient one.
Calibration complete.
And it automatically stops calibrating. Now, nice thing about Vicon is that it does both intrinsic and extrinsic calibration. So now, what you cannot see from the camera, but I will come close, thing is that there's a little bit of leveler here. You see the leveler? And so then we have a couple settings here, and these things that we're going to use this to try to lay flat on the ground. And what it does is detects these IR lights, and it knows the offset from this to the ground, and that's how we set the floor. Similar to how we did it with the calibration board, but in our case, we will be using this. All right. So do you see a pin underneath that you saw earlier? So I've aligned it somewhat to the room. We took a similar point. It doesn't have to be, but whatever this is going to be our orientation of X, Y, and Z. So we just wanted to set it sort of aligned to the room so you have your references correct. So once we have that, we come back here. First, we check the calibration values. These are not bad. Usually I like them to be around 0.1 something, but some of them are 0.2 error, but I will take it for the purposes of this lecture. So now once we have that, we do set volume origin. Our wand is already on the floor. As you can see, all of them are detecting it. A nice thing about Vicon is that when you use the wand, it does both intrinsic and extrinsic at the same time. Okay, so we do start volume calibration. Now it's recording it. And
origin set.
At this point, your cameras are calibrated. So let me go back to my 2 view, and let's look at this guy. So you can see the camera, all the cameras are in green, they're calibrated, and these are the exact position. Now you see DV over here. This is our reference video camera. These are our IR cameras. The rest are IR cameras. So now, here what I will do is I will add a subject model that I created, which was the wand. And once I add the wand, as you can see, you can see it being detected on the screen. So now what I'm going to do is I'm going to go around and wave the wand, and if it is following, if it works, then you can see it even through my body, as long as it can see it. Even though the camera can't see, you can see it through my body because other motion capture markers are detecting it. So as I move them around, no matter how fast it is able to detect it. Now you just completed Vicon motion capture system calibration. Now we will do markerless motion capture camera calibration. In this case, we'll be using Capture intrinsic and extrinsic calibration. So for intrinsic calibration, what we have to do is use the checkerboard for Capture. This is markerless motion capture system. Use the checkerboard and go in front of every board, and here in the user interface, we'll be using the lens over here, the calibrate. So when you turn it on, this user interface will show up. And then under lens, this is intrinsic calibration. There is extrinsic calibration. We'll come back to that later. Intrinsic calibration. Okay, so what we want to do is calibrate all the boards. So we will start capture board calibration, and it will automatically switch to the particular board that we point the calibration board to. So as I move around, nothing really happening, right? So I'm going to go start with this particular camera. Hello, you. Okay, so when I point to it, right now it's showing one screen at a time. We can also make it, so we want to do coverage. Do you see the numbers over there? That's showing depth angle. We want that to be 70% or more, ideally. So you want to move around. It's better to come close and do it so that you can have good coverage. So almost 100% coverage now. This corner here. All right, so what are we looking at in terms of the coverage? Let's see, I can't see the number. So this is 69 and 100% coverage. Okay, so that's close to 70, so we're gonna move on. All right, this camera, so it switches. This is a little bit time consuming, but see, this one's over. This is 100% and 70%, and then the coverage is 70%. We're gonna move on. All right. All of them 100% coverage. Most of them are close to 70% depth angle. So we will stop capturing more. And at this point, it's pretty good coverage. So that's a calibrate lens. It's continuing to calibrate here. And this is your error that's computed. That was real time. Now post calibration step. Now we see that they're all below 1 pixels. This is excellent. We would like to be this way. Okay. All right. So then now we move on to volume calibration. These are your extrinsic calibration. Calibrate all. Capture calibration board. Let's see. Walking around in spiral. Point it down a little bit. Still point it up because the cameras are still high, but they automatically stop at this point. 2.67. I will accept it, and we'll continue. And to set the floor, I put it on the floor already in a specific orientation. I make it parallel to the room. And the blue, green, and red, they will give us our floor axis. So we do set floor. And at this point, it is set in the floor. And then we do one more time, refine. And at this point, we start to see the axis. So now if you go and move, so we're done with the calibration at this point. One way to check how good our calibration is to see the alignment from a given camera. Is it, you scroll in, is it right on the camera? So that's good. So that's telling us that when you scroll up, this is the layout of our camera. And now when we go out, back into the camera, so basically this is very good, right? So if you ever see that the cameras are not on top of each other, then that's a good indication that something might have moved. So this is good. They look good. All right, so that's your camera calibration. I hope you guys learned a lot and eager to try it out yourself in the lab. See you in the lab.